Here we are discussing Stokes Law and the concept of terminal velocity. This is applicable in case of objects which are falling under gravity in a fluid or a liquid. Say for example, we have a very deep container, right, filled with some particular liquid. Say this is filled with liquid throughout, and let us say we have an object, right, an irregular shaped object which is falling in this liquid, due to the effect of gravity, right. Now, when this is falling inside it, the various forces which come into play are W, that is the weight of the object, upthrust acting on it, which we'll denote by FB, because that is buoyant force. The buoyant force which is applied by this liquid onto this particular object as it is coming down, and the viscous forces. The viscous force will denote it by FV. Weight is because of the gravitational pull applied by the earth onto this. It is coming down. Upthrust because of the liquid applying a force in the upward direction. Viscous forces comes into play because when this object starts moving down with certain velocity, the layer of the liquid which is very close to this object starts moving with the velocity of this object, whereas the layers which are away from this move with lesser and lesser speed, and probably this layer moves with nearly zero speed. So there's a velocity gradient in this direction. This layer is moving very fast, this layer is moving very slow. So there is internal friction between these layers of the liquid, and this gives rise to viscous force. That's one. The other fact is that as this object keeps on going down and its velocity keeps on increasing, right, viscous forces keep on increasing. They are directly proportional to the velocity of the object, right. If I try to take an example of translational motion, say for example, if we are moving in a car and say for some time we take our hand out of the window of the car, not certainly recommended, not a good thing to do from a safety perspective, but supposing we are doing that, our experience is that as the speed of the car increases, we feel more force acting on our hand. Right? That is because the wind is applying larger and larger force as the velocity of the car increases. Something similar is happening over here. As this object keeps on going down faster and faster, the viscous forces keep on increasing. Right? Now, the weight is acting in the downward direction, upthrust is acting in the upward direction, and viscous forces always act opposite to the direction of the motion. So they would be acting in the upward direction. So we have downward force and upward force. Now, downward force is W and the upward forces are the buoyant force or the upthrust and the viscous forces. Now, what happens is as the velocity keeps on increasing, Fv keeps on increasing. And at certain stage, what is observed is that these two become equal. Right? Weight is constant, right? Fb is also constant, but as we keep on increasing this, right, at certain point in time, when the value of Fv reaches a certain value, these three become equal, and therefore the net force acting on this particular object which is going down becomes zero. And when force is equal to zero, right, acceleration is zero, and therefore change in velocity is zero, and therefore it starts moving with constant velocity in the downward direction. And this velocity, constant velocity with which it starts going down, right, after some time, is known as the terminal velocity. Or we say the object has achieved terminal velocity. So this is how terminal velocity comes into play. Right? Having got this background as to how terminal velocity comes into play, we'll try to look at it more closely and try to arrive at an equation for terminal velocity. And there we will use Stokes' experimental values. Stokes conducted a number of experiments, and he gave the equation for Fv, for viscous forces, and he said it is equal to 6 pi eta Rv. Let me write down over here, Fv, viscous force is 6 pi eta Rv. Right? Based on experiments, he gave this equation for viscous forces. We'll take this equation as it is, where eta is the coefficient of viscosity of this liquid, right? R is the radius and V is the velocity of the object. Yes, I just forgot to mention one point. Stokes' law, he gave this equation only for, I think I should have mentioned that when I started this, only for spherical objects. So this equation is applicable only for spherical objects because you've got radius r in it. So he conducted these experiments on spherical objects, and he said viscous forces are given by 6 pi eta rv, where eta is the coefficient of viscosity, r is the radius of that spherical object, and v is the velocity with which it is moving. Weight. If we look at weight for a spherical object, we know it is given by volume of the body into density of the body into g. So this will be now volume of the body, because we are looking at a spherical object of radius r. It will be 4 upon 3 pi r cube, which is the volume of a sphere, into density of the body into g. As far as upthrust is concerned, upthrust is vi rho f g, where vi stands for immersed volume, rho f is the density of the fluid. Remember this density of the body, the sphere which is coming down, rho f is the density of the fluid. Vi, in this case, the entire volume is immersed, therefore this will be the same as volume of the body. So you'll get 4 upon 3 pi r cube rho f into g. Now, for equilibrium condition, that means when the object is moving with terminal velocity, we have W is equal to Fb plus Fv. And therefore, I put these equations over here. I'll get 4 upon 3 pi r cube rho bg is equal to 4 upon 3 pi r cube rho fg plus 6 pi eta r v. Right? And from this I can find out the velocity. Right? I'll just rearrange this equation. I'll get 6 pi eta r v is equal to 4 upon 3 pi r cube g rho b minus rho f. Right? I take it on this side and I take this part common. Okay, pi will get cancelled. 1 r is there here. This will become r square, and I can take the 6 over here. So I'll get eta v is equal to 4 upon 6 will come over here. So 6 is 18. Pi is getting cancelled. This is becoming r square. G will remain as it is, and we'll have rho b minus rho f. And therefore, I'll get this equation v is equal to, this will become 2 upon 9. 2 2s are to 9. R square G into rho b minus rho f upon eta. Yes. So we have this equation for terminal velocity. R is, as I said, radius of the sphere. These two are this density of the sphere, this density of the fluid, coefficient of viscosity. And as you can see in this equation, v is proportional to r square. Right? So terminal velocity depends upon radius square. Right? So a small change in radius and the terminal velocity will increase quite a bit. So this is the equation for terminal velocity based on Stokes equation of 6 pi eta rv. This will be applicable, or we can use this equation when rho b is greater than rho f. Right? Density of the body is larger than density of the fluid. If you have density of the fluid greater than density of the body, then what will happen is the object will start moving up. Right? And for example, when air bubble starts moving up inside, for example, an air bubble over here starts moving up and reaches the surface of water, because density of the bubble would be smaller than the density of the object. Okay, with this I have covered Stokes law and terminal velocity. Right? As I always say, before you get into this video, there are certain things that you should be clear about. For example, in this video, we used concepts which we had studied earlier. For example, upthrust, and we have used terms like eta, which we have done in a previous video on viscous forces. So look at those videos once again, right, so that you're able to understand this part very well. Thank you.